Our brains are remarkable. They solve problems, learn new things, and even dream. Scientists and engineers are now building a new kind of computer inspired by the human brain. These brain-like computers are also called neuromorphic computers. They promise to change how we interact with technology. Imagine a computer that thinks more like you do. It can learn from its experiences, adapt to new situations, and make decisions with incredible efficiency. This is the potential of neuromorphic computing. This technology is still in its early stages, but it is already showing great promise in areas like artificial intelligence, robotics, and medicine. Join me as we explore the exciting world of brain-like computers and their potential impact on our future. For decades, computers have relied on a rigid architecture. Central processing units, or CPUs, execute instructions sequentially, like following a recipe step by step. While effective, this approach differs greatly from the brain's intricate workings. The human brain is a complex network of billions of neurons. These neurons communicate with each other through trillions of connections called synapses. This intricate web allows our brains to process information in a massively parallel and interconnected way. Neuromorphic computing draws inspiration from this biological marvel. Instead of relying on separate processing and memory units, it aims to mimic the brain's structure and function. By doing so, it opens up new possibilities for computation. In a brain-like computer, artificial neurons and synapses replace transistors and circuits. These artificial neurons are interconnected in a vast network, much like their biological counterparts. Each connection carries a certain weight, representing the strength of the relationship between two neurons. When a brain-like computer receives information, it activates specific neurons in its network. These activations propagate through the connections, mimicking the way electrical signals travel in the brain. The network learns by adjusting the weights of these connections, strengthening some and weakening others. This process of adjusting connection weights is analogous to how our brains learn. Through experience, our brains rewire themselves, strengthening connections that are frequently used and pruning away those that are not. Brain-like computers aim to replicate this process, allowing them to learn and adapt over time. One of the most remarkable features of the human brain is its plasticity. Our brains are constantly changing and adapting throughout our lives, forming new connections and rewiring existing ones. This plasticity allows us to learn new skills, recover from injuries, and adapt to new environments. Brain-like computers share this capacity for plasticity. As they are exposed to new information and experiences, their artificial neural networks can reconfigure themselves. This allows them to learn from their mistakes, improve their performance, and even develop new capabilities over time. This inherent adaptability makes brain-like computers particularly well-suited for tasks that involve learning, pattern recognition, and decision-making in complex and dynamic environments. They can analyze vast amounts of data, identify patterns, and make predictions with remarkable accuracy. Section 5. Learning like we do. Traditional computers excel at tasks that involve precise calculations and rule-based logic. However, they struggle with tasks that humans find intuitive, such as recognizing faces, understanding natural language, and navigating unfamiliar environments. Brain-like computers, with their ability to learn from data, offer a different approach. They can be trained on massive data sets of images, text, or sensor data, allowing them to develop sophisticated internal representations of the world. For instance, a brain-like computer can be trained to recognize faces by analyzing thousands of images. Through this training process, it learns to identify the subtle features and patterns that distinguish one face from another. This ability to learn from data makes brain-like computers ideal for tasks such as image recognition, natural language processing, and autonomous navigation. Section 6. Beyond the binary. Traditional computers rely on a binary system of zeros and ones to represent information. This system, while effective for many tasks, is fundamentally different from the way the human brain processes information. Our brains operate on a spectrum of analog signals, with neurons firing at different rates and with varying intensities. Brain-like computers aim to mimic this analog nature of the brain. They utilize artificial neurons that can fire at different rates, representing information in a more nuanced and continuous manner. This departure from binary computing allows brain-like computers to process information more efficiently and with greater flexibility. Moreover, brain-like computers can leverage the concept of spiking neurons. These neurons communicate through discrete spikes of electrical activity, similar to the action potentials observed in biological neurons. This spiking behavior enables brain-like computers to process information in a more energy-efficient manner, as energy is only consumed when a neuron fires a spike. Section 7. A revolution in efficiency. One of the most significant advantages of brain-like computers lies in their potential for energy efficiency. Traditional computers consume vast amounts of energy, especially when performing complex computations. Brain-like computers, on the other hand, are designed to operate with significantly less power. This energy efficiency stems from their unique architecture and processing mechanisms. By mimicking the brain's parallel processing and spiking behavior, brain-like computers can perform complex tasks with a fraction of the energy required by traditional computers. This efficiency has profound implications for various fields, particularly for mobile devices, wearable technology, and data centers. Imagine smartphones that can last for days on a single charge, or data centers that consume significantly less energy while processing massive amounts of information. Section 8. Machines with moral implications. The development of brain-like computers raises important ethical considerations. As these machines become more sophisticated and capable of independent decision-making, we must grapple with the implications of their actions. One concern is the potential for bias in their decision-making. Brain-like computers learn from the data they are trained on. If this data reflects existing societal biases, the computer's decisions may perpetuate or even amplify these biases. Another concern is the issue of accountability. If a brain-like computer makes a decision that results in harm, who is responsible? Is it the developers of the technology, the users of the system, or the machine itself? Addressing these ethical dilemmas is crucial as we continue to develop and deploy brain-like computers. We must ensure that these technologies are used responsibly and ethically, with appropriate safeguards in place. Section 9. Competition or collaboration. The emergence of brain-like computers has sparked discussions about their potential impact on the job market. Some fear that these machines could displace human workers in various fields, leading to widespread unemployment. While it is true that brain-like computers excel at certain tasks traditionally performed by humans, it is important to note that these machines are not intended to replace humans entirely. Instead, they are tools that can augment human capabilities and free us from mundane or repetitive tasks. The future likely holds a collaborative relationship between humans and brain-like computers. Humans can leverage the computational power and efficiency of these machines, while machines can benefit from human creativity, intuition, and ethical judgment. Section 10. The future landscape. The field of brain-like computing is rapidly evolving, with new breakthroughs and applications emerging constantly. Researchers are exploring novel materials, architectures, and algorithms to further enhance the capabilities of these machines. One promising area of research is the development of memory stores, which are electronic components that can remember their previous state, similar to synapses in the brain. Memory stores have the potential to revolutionize computing by enabling the creation of highly efficient and compact brain-like computers. Another exciting avenue is the integration of brain-like computers with other emerging technologies, such as quantum computing and nanotechnology. This convergence of technologies has the potential to unlock unprecedented computational power and create entirely new possibilities. Section 11. Our neural future. The development of brain-like computers represents a paradigm shift in computing. These machines, inspired by the intricate workings of the human brain, have the potential to revolutionize various aspects of our lives. From enhancing artificial intelligence and robotics to advancing medicine and scientific discovery, brain-like computers hold immense promise. As we continue to unlock their potential, we can expect to see transformative changes in how we interact with technology and the world around us. However, we must proceed with caution, addressing the ethical implications and ensuring that these technologies are used responsibly. The future of computing is neural, and it is up to us to shape it in a way that benefits all of humanity.